What if you were standing on the surface of another world, gazing up at an alien sky beneath the light of a distant sun? The universe is vast beyond comprehension, yet here we are, tiny specks on a pale blue dot, wondering if we're truly alone. For centuries, humanity has stared at the stars and asked one profound question: is there life out there? Today, that question isn't just philosophical, it's scientific. Thanks to breakthroughs in astronomy, we've discovered thousands of exoplanets orbiting far-off stars, each one a potential cradle for life. But among them, a select few standout worlds with just the right conditions, tucked into what scientists call the habitable zone. These are the planets where liquid water could flow, where atmospheres might cradle delicate chemistry, and where, just maybe, life could take root. Think about that for a moment. Out there, scattered across the galaxy, are 25 known planets that fit this extraordinary profile. They're not just points of light in a telescope, they're places. Some might have vast oceans, others swirling clouds or towering mountain ranges. A few could even harbor something more, something alive. The criteria scientists use to identify these worlds are meticulous: the right distance from their star, the right size, the right composition. It's like piecing together a cosmic puzzle where every clue brings us closer to answering humanity's oldest mystery. This isn't just about science, it's about imagination. It's about stepping into the unknown and daring to ask, what if? As we explore these 25 planets, we're not just cataloging distant rocks, we're rewriting the story of our place in the universe. Are we an accident, a fluke of nature, or is life something far more common, waiting to be found among the stars? Strap in, because today, we're embarking on a journey to the most promising worlds beyond our solar system, places that could redefine what it means to call a planet home. Just 4.24 light-years away, practically next door in cosmic terms, orbits a world that could rewrite our understanding of life beyond Earth. Proxima Centauri b is the closest known exoplanet to us, a rocky neighbor tucked into the habitable zone of its faint red sun. But don't let its familiar size fool you. This place is anything but Earth-like. Its star, Proxima Centauri, is a red dwarf, smaller and cooler than our Sun, but prone to violent outbursts of radiation that could strip away atmospheres and bathe the surface in deadly flares. Here's what makes this planet so fascinating. Because it's so close to its star, a year on Proxima Centauri b lasts just 11 Earth days, but that proximity comes with a catch: tidal locking. One side of the planet likely faces its star forever, basking in eternal daylight, while the other half is trapped in endless night. Imagine a world where the border between scorching desert and frozen wasteland could be the only place where life might cling on. Yet, against all odds, scientists haven't ruled it out. Recent studies suggest Proxima Centauri b might have a thin atmosphere or even vast oceans beneath its icy outer shell. Some models show that if enough heat circulates from the day side to the night side, liquid water could exist in those twilight zones, and where there's water, there's hope. The real question isn't just whether this planet could host life, it's whether anything could survive the star's fury. Those intense flares might blast away any chance of a stable climate, turning the surface into a irradiated wasteland. But life on Earth has thrived in the most extreme places, from volcanic vents to Antarctic ice. Could something just as resilient exist under the crimson glow of Proxima Centauri? Every new telescope, every advanced simulation brings us closer to the answer. This isn't just about one planet. It's a test case, a glimpse into whether red dwarf systems, the most common stars in our galaxy, could be cradles for life. If Proxima Centauri b has even a whisper of habitability, it changes everything. Because if life can take hold here in this harsh and humming system, then the universe might be far more alive than we ever dared to dream. The violent flares erupting from Proxima Centauri aren't just spectacular cosmic light shows, They could be the deciding factor in whether its neighboring planet ever stood a chance at hosting life. These stellar outbursts unleash torrents of X-rays and ultraviolet radiation, powerful enough to rip away an atmosphere molecule by molecule over time. Picture Earth's protective ozone layer being shredded by a relentless solar storm, leaving the surface exposed. That's the daily reality Proxima Centauri b might face. But here's where things get surprising. New climate simulations suggest this planet could defy the odds. Scientists running advanced computer models have discovered something remarkable. If Proxima Centauri b started with a thick enough atmosphere, say one heavier than Earth's, it might cling to it despite the star's fury. The key lies in the planet's possible magnetic field. Just like Earth's magnetic shield deflects solar wind, Proxima Centauri b's own magnetic field could channel those deadly flares around the planet, protecting its air from complete erosion. There's even a chance that atmospheric gases, once stripped away, might be replenished by volcanic activity or chemical reactions in the planet's crust. Then there's the tantalizing question of water. Even with a battered atmosphere, climate models show that certain regions, especially those twilight zones between permanent day and night, could maintain stable temperatures for liquid water to exist. Some simulations predict vast, planet-wide oceans trapped beneath a thick ice shell, kept liquid by geothermal heat or tidal forces flexing the planet's interior. Others suggest brief, seasonal melt cycles where water pools in sheltered craters before refreezing. This is where the James Webb Space Telescope becomes our greatest ally. Soon, its infrared eyes might detect the chemical fingerprints of an atmosphere, or even water vapor lingering around Proxima Centauri b. By analyzing how starlight filters through the planet's potential air layers, Webb could spot telltale molecules like carbon dioxide or methane, which often hint at geological or even biological activity. Every observation brings us closer to solving the puzzle. Is this a scorched wasteland or a world with pockets where life could endure? The implications stretch far beyond one planet. If Proxima Centauri b, battered by radiation and tidal forces, still manages to hold onto the ingredients for habitability, then countless other red dwarf systems, making up 75% of the galaxy's stars, could harbor similar surprises. We might be standing on the brink of a paradigm shift where the universe reveals itself not as a barren expanse, but a place where life fights tenaciously for a foothold, even in the harshest corners. Now picture a star so small and dim, you could barely see it from Earth, yet around it orbits not one, but 7 Earth-sized worlds, all packed into a space tighter than Mercury's orbit around our Sun. Welcome to TRAPPIST-1e, the crown jewel of one of the most extraordinary planetary systems ever discovered. This isn't just another exoplanet. It's a tantalizing puzzle piece in our search for habitable worlds, sitting snugly in the Goldilocks zone of its ultra-cool dwarf star. What makes TRAPPIST-1e so special? For starters, it's almost exactly Earth-size, a rarity among exoplanets, which tend to be either gargantuan gas giants or tiny, scorched rocks. But here, gravity would feel familiar, and the terrain might look eerily recognizable. Scientists believe it's almost certainly a rocky world with a solid surface where water could pool if it exists. And that's the million-dollar question, because while TRAPPIST-1e gets just the right amount of starlight to keep water liquid, its star is a far cry from our steady golden sun. Ultra-cool dwarfs like TRAPPIST-1 are cosmic slow burners, emitting a faint reddish glow and barely any heat. Planets huddle close to stay warm, resulting in years that fly by in just 6 Earth days. But this proximity comes with trade-offs. The star's feeble light might leave TRAPPIST-1e bathed in perpetual twilight, with skies the color of burnt amber. And because the planets orbit so tightly, their gravitational dances could squeeze and flex their interiors, generating heat through tidal forces like Jupiter's moon Europa, but on a planetary scale. Then there's the system's most mind-bending feature, the view from the surface. Imagine standing on TRAPPIST-1e and looking up to see not just one, but 6 neighboring worlds, some larger than the moon in Earth's sky gliding past in a celestial ballet. Some might even show visible features like clouds or ice caps, but this cosmic spectacle hints at a darker possibility. With planets so close, their gravity could tug at each other's atmospheres, or worse, fling catastrophic asteroid impacts across the system. Yet hope isn't lost. The James Webb Space Telescope has already detected hints of water vapor in this system, and TRAPPIST-1e remains a prime target for further study. If its atmosphere holds carbon dioxide or ozone, it could signal an active carbon cycle, or even photosynthesis. The stakes couldn't be higher, because if life can thrive under the faint glow of an ultra-cool dwarf, the galaxy might be teeming with hidden oases waiting in the quiet dark. What truly sets TRAPPIST-1e apart isn't just its Earth-like size, it's the delicate interplay of forces that could make this world a haven for life or a cautionary tale. Let's start with temperature. Unlike scorching Venus or frozen Mars, this planet basks in a remarkably stable equilibrium, hovering around the freezing point of water if it has an Earth-like atmosphere. But here's where things get intriguing. Without an atmosphere, surface temperatures might plummet to -40 degrees Celsius, turning the world into a global icebox. Yet, if TRAPPIST-1e holds onto even a thin blanket of greenhouse gases like carbon dioxide, simulations show its climate could stabilize into something shockingly familiar, with liquid water persisting across vast regions. Then there's the wild card, tidal heating. In our solar system, moons like Io and Europa are stretched and squeezed by Jupiter's gravity, creating volcanic hellscapes or hidden oceans. TRAPPIST-1e experiences something similar, not from a gas giant but from its 6 planetary siblings. Their gravitational tugs could flex the planet's core, generating enough internal heat to keep subsurface oceans liquid for billions of years. Imagine hydrothermal vents spewing minerals into pitch-black waters, much like Earth's deep-sea ecosystems where life thrives without sunlight, but the system's compactness comes with risks. TRAPPIST-1's faint glow is heavy on infrared light, meaning the planets receive less visible sunlight than Earth. While this might sound like a deal-breaker, some microbes on Earth survive solely on infrared radiation, suggesting life here could adapt to the star's dim crimson hue. More concerning is the bombardment of ultraviolet flares. Red dwarfs like TRAPPIST-1 are notorious for violent outbursts, and without a robust magnetic field or thick atmosphere, this planet's surface could be sterilized regularly. Yet recent studies offer a glimmer of hope. Atmospheric models indicate that if TRAPPIST-1e formed with ample water, perhaps delivered by icy comets during its infancy, its oceans might persist beneath a protective ice layer shielded from UV radiation. Even more compelling, the tight orbits of the TRAPPIST-1 planets could lead to atmospheric swapping, where impacts or stellar winds strip gases from one world only for them to be captured by another. Over eons, TRAPPIST-1e might have stolen or inherited enough atmosphere to cling to habitability. The James Webb Space Telescope is peering into this system right now, searching for the chemical fingerprints of water, methane, or oxygen. Any hint that this world isn't just another frozen rock. If it finds them, the implications are staggering, because if life can emerge around a star 1,000 times dimmer than our Sun, then the galaxy's quiet corners might be far more vibrant than we ever imagined. Stretching across the vast cosmic ocean, 1,200 light-years from Earth, orbits a world that might just be one of the most promising candidates for habitability we've ever found, Kepler-442b. This isn't just another exoplanet lost in the data of telescopes. It's a super-Earth, a class of planet that's tantalizingly close to the sweet spot for life as we know it. With a radius 1.3 times that of our own planet, Kepler-442b sits right on the edge of what scientists consider the perfect size, big enough to hold onto a thick atmosphere, but not so massive that it becomes a crushing mini Neptune with no solid surface. But what really sets this world apart is its star. Unlike the volatile red dwarfs we've seen so far, Kepler 442b orbits a K-type star, a stable, orange-hued sun that's less tempestuous than our own. Imagine a star with the warmth of a sunset that never fades, bathing its planet in gentle, golden light for billions of years. These K-type stars are the quiet achievers of the galaxy, burning slower and living longer than even our sun. While Earth's star might one day expand into a red giant and scorch our world, Kepler 442b's host could keep its habitable zone stable for tens of billions of years, giving life an unimaginable head start to emerge and evolve. Then there's the gravity. With an estimated surface pull about 30% stronger than Earth's, walking on Kepler 442b would feel like carrying a heavy backpack, challenging but not impossible. This extra gravity could help the planet retain a thick atmosphere, shielding it from cosmic rays and maintaining the pressure needed for liquid water. But it's not just about survivability, it's about potential. A slightly denser atmosphere might mean more efficient air circulation, distributing heat evenly across the planet and preventing the kind of extreme temperature swings that would turn a world into a frozen desert or a scorched wasteland. Here's where the habitable zone comes into play. Kepler 442b orbits at just the right distance to receive about 70% of the sunlight Earth gets, roughly equivalent to Mars in our own solar system. That might sound chilly, but with the right mix of greenhouse gases in its atmosphere, this planet could trap enough heat to keep vast oceans from freezing over. Some climate models even suggest its surface conditions might resemble Earth's northern latitudes, cool but brimming with liquid water. The big question, of course, is whether Kepler 442b has that crucial ingredient, water. While we can't peer directly at its surface yet, the planet's size and position make it a prime candidate for hosting vast reservoirs. And with its star's steady, predictable output, any life that did emerge wouldn't have to contend with the violent flares or tidal locking that plague planets around red dwarfs. It's the kind of stability that could allow complex ecosystems to flourish over geological timescales. Kepler 442b stands as a reminder that habitability isn't just about being in the right place, it's about having the right conditions, the right star, and the right time. In a universe where so many worlds are either too hot, too cold, or too turbulent, this distant super-Earth offers something rare, a glimmer of cosmic balance. And as our telescopes grow more powerful, this world so far away yet so full of promise might just become the benchmark against which we measure all other habitable candidates. Deep in the constellation Cetus, orbiting a dim red star just 40 light-years from Earth, lies a world that defies the odds, LHS 1140b. This isn't just another exoplanet lost in the shuffle. It's a heavyweight champion of the habitable zone, a dense, rocky giant with twice Earth's mass packed into a surface only 20% larger. Picture standing on a planet where everything feels more gravity stronger, landscapes more rugged, skies, if they exist, thicker with air. That's the tantalizing reality of LHS 1140b, a super-Earth that might just hold onto something precious, an atmosphere capable of nurturing life. What makes this world stand out isn't just its size, it's the star it calls home. Unlike the violent flares of Proxima Centauri or TRAPPIST-1, this red dwarf is unusually calm for its kind, emitting a steady, faint glow with only occasional flickers of activity. That stability is a game-changer. While most red dwarfs bombard their planets with enough radiation to strip away atmospheres over time, LHS 1140b might have been spared the worst, giving it a fighting chance to hold onto its air. Scientists compare it to weathering a storm behind a sturdy shield. Where other worlds might be left exposed, this one could endure. Then there's the planet's extraordinary density. Calculations suggest it's made of rock and metal with a composition eerily similar to Earth's core. But here's the twist. That density might hint at vast reservoirs of water trapped beneath the surface, or even a global ocean sealed under miles of ice. Some models propose a water world scenario where the sheer weight of the planet's gravity keeps liquid stable despite the star's weak warmth. Others speculate about a thick, Venus-like atmosphere, heavy with carbon dioxide, creating a greenhouse effect strong enough to maintain liquid water on the surface. The real excitement, though, lies in what we might soon discover. The James Webb Space Telescope has already turned its gaze toward LHS 1140b, searching for the faint chemical signatures of an atmosphere. Key targets include water vapor, carbon dioxide, or even methane molecules that could hint at geological activity or just maybe biological processes. Every flicker of light passing through the planet's potential air layers carries clues, like a cosmic fingerprint waiting to be decoded. But the mysteries don't end there. If this super-Earth does have a substantial atmosphere, how did it survive the star's early years when red dwarfs are known to be especially violent? One theory suggests LHS 1140b might have formed farther out, migrating inward only after its star settled into calmer middle age. Another possibility is that volcanic activity continually replenishes lost gases, much like Earth's tectonic cycles. Whatever the answer, this world challenges our assumptions about red dwarf systems, proving they aren't all dead zones. Some might be hidden oases in the dark. LHS 1140b isn't just a scientific curiosity, it's a test of resilience. If a planet this massive, this close to a red dwarf, can cling to the ingredients for habitability, then the galaxy's most common stars might host far more life-friendly worlds than we ever imagined. And with every new observation, we're not just studying a distant dot of light, we're probing the boundaries of what's possible in the universe. Hidden in the quiet constellation of Aries, just 12 light-years from Earth, orbits a world that's practically whispering to us across the cosmic dark, Teegarden star B. This isn't just another exoplanet, it's a time capsule, a relic from an era when the universe itself was young. Discovered in 2019, this Earth-mass planet circles one of the smallest, coldest stars known to science, a red dwarf so faint it wasn't even spotted until 2003. But don't let its dim glow fool you. Teegarden star B is a paradox, a planet that could be both frozen in time and teeming with possibility. What sets this world apart is its star's eerie calm. Unlike the violent tantrums of Proxima Centauri or even TRAPPIST-1, Teegarden's star is a cosmic monk, radiating so little energy that its habitable zone huddles alarmingly close, about 5% of Earth's distance from the Sun. At that range, tidal locking is almost inevitable, meaning one side of the planet might be forever scorched by a dull, ruby sun while the other languishes in eternal night. Yet here's the twist: despite these extremes, models suggest that with a thick enough atmosphere, heat could circulate enough to create a sliver of temperate real estate along the twilight zone. And where there's stability, there's hope for water and perhaps life. But the real marvel isn't just where Teegarden star B is, but when it formed. This system is ancient, over 8 billion years old, nearly twice the age of our solar system. That means this planet has had more than twice as long as Earth for life to emerge, adapt, and potentially evolve into something complex. Imagine a biosphere that's had 8 billion years to perfect survival strategies, perhaps in subsurface oceans or within radiation-shielded caves. While Earth's earliest microbes were just figuring out photosynthesis, life on Teegarden star B, if it exists, could have already passed through epochs we can scarcely imagine. Detecting that life, though, is a challenge of cosmic proportions. Teegarden's star emits less than 1% of our Sun's visible light, forcing any potential biosignatures, like oxygen or methane, to scream into a void our telescopes struggle to hear. Even the James Webb Space Telescope strains to pass such faint signals, but if we could spot them, the implications would be staggering. A biosignature here wouldn't just hint at life, it would suggest life's ability to endure, to persist across timescales that dwarf human history. Teegarden's star B forces us to rethink the limits of habitability. If life can cling on here in the feeble warmth of an ancient, half-dead star, then the galaxy might be littered with worlds where biology has learned to thrive in the quietest, darkest corners. This isn't just a planet, it's a testament to patience, a reminder that the universe has been experimenting with life far longer than we've been around to notice. And as we stare into the dim red glow of Teegarden's star, we're not just looking at another world, we're peering into deep time itself. 500 light-years away, tucked into the constellation Cygnus, drifts a world that made history, K2-18b. This wasn't just another exoplanet discovery. It was the first time humanity laid eyes on an Earth-sized world sitting snugly in the habitable zone of another star. Picture a planet so similar in size to ours that if you stood on its surface, the horizon might feel hauntingly familiar. Yet the sky above would tell a very different story. Kepler-186f orbits a star far smaller and cooler than our Sun, a faint M dwarf glowing with just 4% of the Sun's brightness. But here's the twist, this planet is so close to its star that a full year passes in just 130 Earth days, bathing it in perpetual twilight. What makes Kepler-186f so groundbreaking isn't just its size. It's what that size implies. With a radius only 10% larger than Earth's, this world almost certainly has a rocky surface, not the crushing gas layers of a mini Neptune. Gravity here would feel nearly identical to home, making it one of the few exoplanets where walking wouldn't be a struggle, but the similarities might end there. M dwarfs like Kepler-186 are notorious for their violent youth, bombarding nearby planets with radiation during their early billion years. If this planet started with an Earth-like atmosphere, much of it could have been stripped away long ago, leaving behind a desiccated shell, yet hope isn't lost. Recent climate models reveal a fascinating possibility. Even with a thin atmosphere, Kepler-186f's tight orbit might keep temperatures just right for liquid water, if the air contains enough carbon dioxide to trap heat. Imagine a world where the sun hangs low and red in the sky, casting weak, crimson light over vast, shallow seas. Or perhaps the planet's axis tilts dramatically, creating seasons so extreme that water only flows during brief, scorching summers before freezing into glaciers. The real challenge is the star's temperament. M dwarfs may be small, but they're unpredictable, frequently unleashing flares that could scour the planet's surface of life. Without a robust magnetic field, something we can't yet detect from Earth, Kepler-186f, might be a beautiful but barren world. But if it holds onto even a fraction of its original atmosphere, or if underground reservoirs have sheltered microbial life, this planet could rewrite our understanding of where life can thrive. Kepler-186f stands as a reminder that Earth's twin might not look like Earth at all. It could be a world of twilight skies and quiet oceans where life clings on in ways we're only beginning to imagine. And as telescopes grow more powerful, this distant, Earth-sized enigma might finally reveal whether it's a cosmic mirror or a glimpse of how strange and resilient life in the universe truly can be. Just 31 light-years from Earth, in the constellation Hydra, orbits a world that blurs the line between familiar and alien GJ 357d. This isn't just another exoplanet, it's a cosmic paradox, a super-Earth caught between two identities. With a mass at least 6 times greater than our planet, GJ 357d could be a rocky giant with towering mountains and deep, sprawling oceans, or a shrouded mini Neptune, its surface hidden beneath layers of thick, swirling gas. What makes this world so captivating isn't just its size or distance, it's the tantalizing possibility that it might defy expectations entirely. The key to unlocking GJ357D's secrets lies in its orbit. Nestled in the outer edge of its star's habitable zone, this planet receives about as much stellar energy as Mars does from our Sun. On paper, that sounds chilly, but here's where the atmosphere comes into play. If GJ357D has a dense blanket of greenhouse gases like carbon dioxide or methane, it could trap just enough heat to keep water liquid. Picture a world where the air itself acts like an insulating cloak, turning what should be a frozen wasteland into a temperate haven. But the debate rages on. Is this a planet we'd recognize or something stranger? Some models suggest it's a scaled-up version of Earth with a molten core and active geology that could recycle gases through volcanoes. Others argue its mass points to a watery reality, a global ocean hundreds of miles deep capped by a crushing atmosphere. Then there's the mini-Neptune scenario where the surface isn't solid at all, but a murky transition between gas and slushy ice. The star it circles adds another layer of intrigue. GJ357 is an M-dwarf, smaller and cooler than our Sun, but unlike many of its volatile siblings, this one is remarkably quiet, a rarity that could have spared the planet from atmospheric erosion. That stability might be the reason GJ357D still clings to its air, if it has any at all. What excites scientists most is the prospect of peering into its atmosphere, if it exists. The James Webb Space Telescope could soon analyze starlight filtering through GJ357D's potential air layers, hunting for traces of water vapor or carbon dioxide. Every molecule detected would bring us closer to answering the ultimate question. Is this a world where chemistry could tip toward life, or a fascinating dead end? GJ357D challenges our definitions of habitability. It's a reminder that the universe doesn't always fit into neat categories. Sometimes, the most promising worlds are the ones that force us to rethink everything we thought we knew. Imagine a world where the sky isn't blue, but a hazy, golden shroud of hydrogen where the oceans stretch endlessly, but there's no land to stand on, just crushing depths beneath an atmosphere thicker than anything on Earth. Welcome to K2-18b, a planet that defies every Earth-like expectation. Orbiting a dim red dwarf star 110 light-years away, this isn't just another exoplanet, it's a Hycean world, a term scientists coined for planets with hydrogen-rich atmospheres and vast global oceans. What makes K2-18b so groundbreaking? In 2019, astronomers announced something unprecedented. They'd detected water vapor in its atmosphere. Not just traces, but significant amounts enough to suggest this planet isn't just a barren rock or a gas giant, but a place where water exists in quantities that dwarf Earth's oceans. Picture an entire world where the humidity is so dense, the air itself feels like a warm, wet blanket. But here's the catch: these aren't oceans as we know them. Without a solid surface, the water likely transitions gradually from vapor to liquid to something stranger, a supercritical fluid under immense pressure where the line between liquid and gas blurs entirely. The sheer weight of K2-18b's atmosphere is hard to fathom. Estimates suggest it could be hundreds of times thicker than Earth's, with pressures so intense they'd crush submarines like tin cans. Yet within that crushing embrace, something remarkable might exist: life. Hycean worlds like this one could harbor microbial organisms in their upper atmospheres, floating in layers where temperatures and pressures are just mild enough to allow chemistry to unfold. Some scientists speculate that beneath the haze, where sunlight filters weakly through the hydrogen layers, photochemical reactions could create the building blocks for life, no solid ground required. But the challenges are staggering. Red dwarfs like K2-18b's star are notorious for their violent flares, which could strip away atmospheres over time. And without a magnetic field, something we can't yet confirm, the planet might be slowly losing its life-sustaining envelope to space. Then there's the question of energy. On Earth, life thrives near hydrothermal vents or sunlight, but here the ocean's surface might be so deep and dark that photosynthesis is impossible. Any organisms would need to rely on chemical energy, perhaps from reactions between water and the planet's rocky core far below. The true significance of K2-18b isn't just that it has water, it's that it represents an entirely new category of habitable world. We've spent centuries imagining Earth-like planets as the only places life could exist, but this Hycean planet shatters that assumption. It forces us to ask, could life evolve in an ocean without shores, under a sky without oxygen? As the James Webb Space Telescope turns its gaze toward K2-18b, searching for molecules like dimethyl sulfide, a gas produced by marine life on Earth, we might be on the verge of answering that question. And if the answer is yes, the galaxy could be filled with hidden oceans, waiting in the golden haze of distant suns. Beneath the swirling golden haze of K2-18b's hydrogen atmosphere, scientists suspect something even more extraordinary, an ocean so vast it could make Earth's seas look like puddles. But this isn't just water as we know it. At the pressures found on this super-Earth, the boundary between liquid and gas blurs into something alien. Picture an abyss where the ocean doesn't have a surface in the traditional sense. Instead, the hydrogen atmosphere gradually thickens until it merges seamlessly with the water below, creating a global fluid layer where the very idea of shorelines becomes meaningless. The real mystery is what happens deeper down. On Earth, hydrothermal vents crackling with geothermal energy support entire ecosystems in pitch-black darkness. These oases of life thrive not on sunlight, but on chemicals hydrogen sulfide and methane bubbling up from the planet's molten core. K2-18b could harbor something eerily similar. If this world has a rocky core beneath its ocean, geothermal heat or tidal forces from its star might fuel hydrothermal activity on a scale we can barely imagine. The catch, any life here would need to withstand pressures hundreds of times greater than the deepest ocean trenches on Earth, in waters so dense they behave more like a supercritical fluid than a liquid. Yet nature has a habit of surprising us. On Earth, extremophiles called piezophiles flourish under crushing pressures, their cellular structures adapted to resist being squashed flat. If similar organisms exist on K2-18b, they might cluster around vents spewing minerals into the dark, their biochemistry tuned to an environment where water behaves in ways we've never seen. Some scientists speculate that in such high-pressure conditions, life could rely on solvents other than water, perhaps liquid hydrocarbons or ammonia, reshaping our very definition of a habitable zone. Then there's the tantalizing possibility of a twilight biosphere. In the upper layers of K2-18b's ocean, where pressures are milder and starlight filters weakly through the hydrogen haze, photosynthetic organisms might eke out an existence. These wouldn't be plants as we know them, but something stranger, microbes harvesting energy from the faint glow of their red dwarf sun, or even from chemical reactions in the atmosphere itself. It's a reminder that life, when given billions of years and a canvas as vast as a planet, can adapt to realms we'd consider hellish. The discovery of K2-18b forces us to rethink not just where life could exist, but what forms it might take. If a world like this, with no solid surface, a crushing atmosphere, and an ocean-defying physics, can harbor even the simplest organisms, then the galaxy's definition of habitable just got a lot wider. Every strange, swirling layer of this alien sea whispers a challenge. Life isn't bound by Earth's rules. It only needs opportunity, time, and the barest whisper of energy to stake its claim in the cosmos. Somewhere in the vast expanse of space, 100 light-years from Earth, spins a world that could be the closest thing we've found to a mirror of our own TOI 700D. Discovered by NASA TESS telescope in 2020, this Earth-sized planet isn't just another dot in the cosmos. It's a tantalizing puzzle with pieces that fit almost too perfectly. Orbiting a calm M-dwarf star, K2-18b sits squarely in the habitable zone, receiving just enough warmth to keep water liquid if it exists. But here's what makes this planet extraordinary. Its star is one of the quietest red dwarfs ever observed, a cosmic neighbor that doesn't bombard its planets with the violent flares that typically strip away atmospheres. For the first time, scientists have an Earth-sized target where the star's serenity might just give life a fighting chance. Yet K2-18b isn't a perfect twin. Like most planets orbiting M-dwarfs, it's almost certainly tidally locked, with one side forever bathed in dim, reddish light and the other shrouded in eternal night. At first glance, that sounds like a recipe for extremes. A scorching desert on one hemisphere, a frozen wasteland on the other. But climate models reveal something surprising. Between these two brutal zones, there could be a narrow band of twilight where temperatures are just right. Picture a perpetual dawn where the sun hangs motionless on the horizon, casting long shadows over rolling landscapes. If K2-18b has an atmosphere capable of circulating heat, this temperate strip could span thousands of miles, offering a refuge for liquid water and perhaps even life. The real excitement lies in what we might soon learn. Unlike many exoplanets, K2-18b is close enough and its star quiet enough for the James Webb Space Telescope to study its atmosphere in unprecedented detail. Scientists are already planning observations to hunt for traces of water vapor, carbon dioxide, or even methane molecules that could hint at geological activity or biological processes. But there's a catch. If the planet's air is too thin, or if its early history was marked by atmospheric loss, those signals might be faint or gone entirely. Every flicker of light Webb captures will be a clue, a whisper from across the stars telling us whether this world is a barren rock or something far more promising. K2-18b represents something rare in the search for habitable planets, a best-case scenario. It's the right size, the right temperature, and orbits the right kind of star. But it's also a reminder that habitability isn't just about checking boxes, it's about the delicate interplay of forces we're only beginning to understand. As telescopes grow more powerful, this distant world might become the benchmark for what we consider Earth-like, proving that even in the quietest corners of the galaxy, the conditions for life can emerge in ways we never expected. 14 light-years from Earth, practically our cosmic backyard, orbits a world that could be one of our best shots at finding life beyond the solar system, Wolf 1061c. This super-Earth, nearly 4 times the mass of our own planet, is a study in contrasts. It's close enough that future telescopes might one day map its surface, yet its environment could be as hostile as Venus or as welcoming as a tropical archipelago. The answer lies in a delicate balance, one that hinges on its precarious position at the inner edge of its star's habitable zone. Wolf 1061c's star is a red dwarf, smaller and cooler than our Sun, but far from docile. Unlike the steady glow of Earth's sun, this star flickers unpredictably, its brightness swinging by up to 10% over short periods. For a planet orbiting so close, completing a full year in just 18 Earth days, these fluctuations could be catastrophic. Imagine a climate where the sun's mood swings dictate whether oceans boil or freeze, where atmospheric chemistry shifts violently with every stellar tantrum. That's the reality Wolf 1061c might face. Then there's the planet's size. With a radius roughly 1.6 times Earth's, it sits on the knife's edge between a rocky super-Earth and a mini Neptune. Gravity here would feel about 70% stronger than home, enough to make every step a workout, but not so crushing that it would preclude life. Crucially, its density suggests a solid surface, possibly dotted with active volcanoes or vast tectonic plates recycling gases through the atmosphere. But here's the catch, that same atmosphere could be its undoing. Because Wolf 1061c skirts the inner rim of the habitable zone, even a slight greenhouse effect might tip it into a runaway scenario. A bit too much carbon dioxide, and the planet could spiral into a Venus-like inferno, its oceans evaporating into space as temperatures soar. Alternatively, if it holds onto just enough water and air, it might mirror early Earth with steamy tropics and swirling storm systems. The difference between paradise and wasteland could come down to atmospheric chemistry we can't yet measure. What makes this world extraordinary isn't just its mysteries, it's our ability to solve them. At 14 light-years, Wolf 1061c is one of the closest potentially habitable exoplanets known, putting it squarely in the crosshairs of next-generation telescopes. The European Southern Observatory's extremely large telescope, set to open its eye to the sky in 2028, could analyze this planet's atmosphere for signs of water, methane, or even industrial pollutants. Every observation brings us closer to answering whether this nearby super-Earth is a cautionary tale or a beacon of hope, proof that life might thrive right next door. Far across the galaxy, 1,400 light-years from Earth, orbits a world that feels almost hauntingly familiar, Kepler 452b. Scientists call it Earth's cousin, and for good reason. This planet doesn't just sit in the habitable zone of its star. It circles a sun almost identical to our own, a golden G-type star burning with the same steady warmth that nurtured life on our world. But here's what makes Kepler 452b extraordinary. It's the closest match we've found to an Earth-sized planet orbiting a sun-like star, a cosmic mirror reflecting what our own world might look like under slightly different circumstances. With a diameter just 60% larger than Earth's, Kepler 452b straddles the line between super-Earth and mini-Neptune, a distinction that could mean the difference between a rocky paradise and a gassy enigma. The planet's mass suggests it could have active geology, with volcanoes churning out atmospheres and tectonic plates recycling minerals. But without direct measurements, scientists are left debating. Is this a scaled-up version of home with towering mountains and deep blue oceans, or a shrouded world hiding its secrets beneath thick layers of hydrogen and helium? Then there's the star itself, Kepler 452, a sun so similar to ours that its light would feel familiar on your skin, its golden hue casting shadows almost indistinguishable from an earthly afternoon. But there's one crucial difference. This star is older. At 6 billion years, it's 1.5 billion years senior to our Sun, meaning any life on its planet has had an extra cosmic head start to evolve. Imagine ecosystems with 1 billion more years of trial and error, of adaptation and complexity. The possibilities are dizzying, yet Kepler 452b's orbit tells a story of quiet resilience. A year here lasts 385 Earth days, just 20 days longer than ours, placing it in a spot where liquid water could flow as easily as it does in our own rivers and lakes. Climate models suggest that with an Earth-like atmosphere, temperatures might hover in a comfortable range, though the planet's extra size could mean stronger gravity and denser air, turning gentle breezes into relentless winds. The real challenge is the distance. At 1,400 light-years, even our most powerful telescopes struggle to glimpse details. Detecting an atmosphere would require observing the planet as it transits its star, watching for the faintest dimming of starlight as molecules like oxygen or carbon dioxide absorb specific wavelengths. So far, the data remains frustratingly silent, but future missions like the Habitable Worlds Observatory could change that, peering into Kepler 452b's skies with unprecedented clarity. What makes this world so compelling isn't just its similarities to Earth, it's the questions it forces us to confront. If a planet so familiar exists around a star so like our Sun, how many others are out there? And if life did take root here, what would 6 billion years of evolution look like? Kepler 452b isn't just a scientific target, it's a glimpse into an alternate timeline, a reminder that Earth might not be unique, just one thread in a vast cosmic tapestry of habitable worlds. Nestled in a cosmic ballet of 3 stars, 23 light-years from Earth, GJ 667cc defies expectations at every turn. This super-Earth, nearly 4 times our planet's mass, orbits the smallest member of a triple-star system, a faint red dwarf that bathes it in perpetual crimson twilight. But here's where the story gets fascinating. While 2 additional stars pirouette in the distance, their combined light is little more than a faint shimmer in GJ 667cc's skies. The real action happens close to home, where this rocky world's tight orbit, just 28 Earth days, places it squarely in the habitable zone of its primary star. What makes GJ 667cc so remarkable isn't just its position, it's the delicate stability it might achieve despite its chaotic stellar neighborhood. Climate models suggest that the gravitational pull of the outer stars is too weak to disrupt the planet's orbit significantly, leaving its climate surprisingly steady. Imagine a world where 3 suns dance on the horizon, yet the primary star's gentle glow dominates, maintaining conditions where liquid water could persist. Some simulations even propose that the distant star's subtle heating effects might counteract the red dwarf's cooler output, creating a temperate equilibrium rare in multi-star systems. Yet GJ 667c's discovery was anything but straightforward. Initial observations in 2011 hinted at its existence, but skeptics dismissed the signals as stellar activity masquerading as a planet. It took years of meticulous follow-up studies to confirm this world wasn't just a ghost in the data. The breakthrough came when astronomers noticed slight wobbles in the star's motion, telltale tugs from GJ 667c's gravity. Even then, debates raged. Was this a dry, rocky super-Earth or a volatile, rich water world with global oceans? The intrigue deepened when researchers detected potential atmospheric clues. While too faint for definitive confirmation, spectral hints suggested GJ 667cc might harbor carbon dioxide or nitrogen gases that could regulate temperatures across its tidally locked surface. On the day side, where the red dwarf hangs motionless in the sky, thick clouds might reflect just enough heat to prevent a scorching desert. Meanwhile, on the frigid night side, atmospheric circulation could transport warmth, creating a narrow band of habitable real estate along the twilight edge. But the greatest mystery lies in its origins. How did a planet this massive form so close to its star without becoming a gas-covered mini-Neptune? One theory suggests GJ 667cc might have migrated inward after birth, shedding its hydrogen envelope along the way. Another proposes it accreted material differently due to the complex gravitational dance of its triple-star nursery. Every unanswered question makes this world a laboratory for testing how planets assemble in the universe's most chaotic environments. GJ 667cc challenges our assumptions about where life could take root. If a world orbiting 3 stars, one of them temperamental, the others distant spectators, can maintain the delicate balance for habitability, then the galaxy's real estate might be far more forgiving than we ever imagined. As telescopes grow sharper, this enigmatic super-Earth could teach us that cosmic harmony isn't about solitude, but resilience, the ability to thrive even when the universe throws everything at you at once. 42 light-years from Earth, drifting in the constellation Pictor, swings a world that defies simplicity, HD 40307G. This isn't just another exoplanet. It's a study in celestial extremes, a super-Earth caught in a gravitational tango with its orange-hued K-type star. What sets this world apart isn't just its placement in the habitable zone. It's the wild, elliptical path it takes to get there. Unlike Earth's nearly circular orbit, HD 40307G follows a stretched, egg-shaped trajectory, swinging close to its star before retreating to colder depths. The result, seasons unlike anything we know: brief, scorching summers where temperatures skyrocket, followed by long, glacial winters that could freeze continents solid. Yet here's the paradox. This very eccentricity might be the key to its potential habitability. A thick atmosphere, think 10 times denser than Earth's, could act as a planetary thermostat, absorbing heat during the close approach and slowly releasing it during the frigid retreat. Picture a world where roiling storms redistribute warmth across latitudes, where jet streams whip furiously to balance the star's uneven heating. Climate models suggest that under the right conditions, HD 40307G might even maintain liquid water year-round, with equatorial regions staying temperate while polar zones oscillate between thaw and deep freeze. The star itself is another piece of the puzzle. K-types like HD 40307 are the unsung heroes of the galaxy, smaller and cooler than our Sun, but far more stable than the flare-prone red dwarfs that dominate exoplanet discoveries. Their golden-orange glow bathes planets in gentle, steady light for tens of billions of years, offering a longevity that dwarfs our Sun's lifespan. For a world like HD 40307G, that means time, lots of it, for chemistry to experiment with life. But observing this planet is no simple feat. At 42 light-years, it's distant enough to challenge even our most advanced telescopes, yet tantalizingly close for future instruments. The European Extremely Large Telescope, slated for completion in 2028, could analyze starlight filtering through HD 40307G's atmosphere, if it has one. The hunt is on for molecules like water vapor or carbon dioxide, which would signal not just habitability but active climate cycles. Every flicker of data from this distant world carries a whisper of possibility, that even in the chaos of an eccentric orbit, nature might find a way to carve out stability. HD 40307G forces us to rethink the rules. If a planet with such dramatic swings can still harbor the ingredients for life, then the galaxy's habitable real estate might be far more diverse and resilient than we ever imagined. It's a reminder that life, if it exists out there, could thrive in places where Earth standards don't apply, where seasons are extreme, skies are alien, and the very definition of home stretches beyond our narrow experience. 11 light-years from Earth, tucked quietly into the constellation Virgo, orbits Ross 128b, a world that stands out in the search for habitable planets for one game-changing reason. Its star is a cosmic pacifist. Unlike the temperamental red dwarfs we've encountered so far, Ross 128 is eerily calm, with barely a flicker of the violent flares that typically strip nearby planets of their atmospheres. That serenity makes Ross 128b a rare gem, a rocky world bathed in steady crimson light, where life might have the luxury of time to emerge and evolve without the constant threat of stellar tantrums. What makes this planet so compelling isn't just its tranquility, it's the numbers. Ross 128b clocks in at just 1.35 times Earth's mass, almost certainly a rocky super-Earth with a solid surface where water could pool. Its orbit is snug, with a year lasting a mere 9.9 Earth days, but here's the twist. Because its star is so dim and cool, that tight orbit still lands it squarely in the habitable zone. Climate models suggest surface temperatures could hover around -60 degrees Celsius without an atmosphere, but add even a thin blanket of greenhouse gases, and suddenly, pockets of liquid water become plausible. The real magic lies in the star's stability. Most red dwarfs spend their youth blasting planets with radiation, but Ross 128 skipped that phase entirely. Observations spanning decades reveal no significant flares, no violent outbursts, just a steady, faint glow. For Ross 128b, that could mean holding onto an atmosphere for billions of years, a rarity in red dwarf systems. Picture a world where the sky is a perpetual shade of twilight, the air thick with nitrogen or carbon dioxide, and the landscape sculpted by slow, geological processes rather than stellar chaos. But mysteries remain. Is this planet tidally locked, with one side forever facing its star and the other locked in darkness? or does it rotate just enough to distribute heat more evenly? Simulations hint that even with tidal locking, atmospheric circulation could create temperate zones along the terminator line, the border between day and night. And if Ross 128b has oceans, tidal forces from its star might keep them liquid beneath icy shells, much like Jupiter's moon Europa. The search for answers is already underway. Next-generation telescopes could soon analyze the chemical fingerprints of Ross 128b's atmosphere, if it exists. The presence of oxygen or methane would be groundbreaking, suggesting not just habitability but possibly even biosignatures. At just 11 light-years away, this world is practically next door in cosmic terms, close enough that future missions might one day study it directly. Ross 128b challenges the narrative that red dwarf planets are doomed to sterility. It's proof that under the right conditions, even the faintest stars can nurture worlds where life might take root quietly, patiently, far from the violent dramas of the cosmos. And if we ever find evidence of life here, it won't just rewrite the rules of astrobiology. It'll remind us that sometimes the most promising worlds aren't the loudest but the ones that whisper. 1,200 light-years from Earth in the constellation Lyra drifts a world that might be the closest thing we've found to an Earth twin, Kepler-62f. This isn't just another exoplanet, it's the outermost of 5 known planets orbiting a star slightly smaller and cooler than our Sun, a quiet K-type dwarf glowing with a gentle orange hue. What makes Kepler-62f extraordinary isn't just its size, just 40% larger than Earth, but its position, perched perfectly in the habitable zone, where liquid water could exist for billions of years without boiling away or freezing solid. Imagine standing on the surface of this distant world. The sun in the sky would appear smaller and dimmer than ours, casting a muted, amber light over landscapes we can only guess at. With a year lasting 267 Earth days, seasons here would unfold slowly, their rhythms dictated by an orbit more elliptical than Earth. Some climate models suggest this could create dramatic shifts between warm and cool periods, while others propose that a thick atmosphere might smooth out these extremes, creating a global climate as stable as our own. Then there's the question of water. Kepler-62f's size and distance from its star make it a prime candidate for hosting vast oceans, perhaps even global ones. Without direct observations, we can't be certain, but if this planet formed with Earth-like proportions of water, its slightly stronger gravity could hold onto every drop, resulting in deeper seas and taller waves. Alternatively, if it's more water-rich than Earth, we might be looking at a world with no dry land at all, a single shimmering ocean broken only by the occasional ice cap or volcanic island. But the most fascinating variable is time. Kepler-62 is an ancient star, 7 billion years old, 2 billion years older than our Sun. That means any life on this planet has had an unimaginable head start. Simple microbes could have evolved into complex organisms long before Earth's first multicellular life even appeared. Picture ecosystems shaped by eons of adaptation, creatures tuned to the star's dim light, perhaps developing bioluminescence to navigate the perpetual twilight. If photosynthesis exists here, it might operate at wavelengths we'd find foreign, harnessing the star's reddish glow in ways no earthly plant ever could. The challenges, though, are real. K-type stars like Kepler-62 are stable, but they still emit enough ultraviolet radiation to threaten early life. Without an ozone layer or a robust magnetic field, the planet's surface could be a harsh place for biology to gain a foothold. Yet life on Earth has proven resilient, thriving in everything from acidic hot springs to Antarctic ice. If Kepler-62f has geothermal vents or subsurface oceans, life might have found refuge there, hidden from the star's occasional flares. What truly captivates scientists is the system itself. With 5 known planets, 2 of them in the habitable zone, Kepler-62 presents the possibility of a multi-world oasis. If life exists on Kepler-62f, could it also have taken root on its sibling, Kepler-62e? And if so, might the 2 planets have exchanged material through asteroid impacts, seeding each other with the building blocks of biology? It's a scenario that transforms this distant system from a collection of rocks into a dynamic, interconnected web of potential. Kepler-62f stands as a testament to patience, a world sculpted by the slow hand of cosmic time, offering us a glimpse of what Earth might become in another billion years. As we study it, we're not just searching for life, we're peering into a possible future, a reminder that the universe's story is far longer and richer than our fleeting chapter in it. 40 light-years from Earth, shrouded in perpetual mist, drifts a world that redefines the term ocean planet, GJ-1214b. This isn't just another exoplanet. It's a pressure cooker of a world where the very air is so thick with water vapor that it's less an atmosphere and more a global steam bath. Scientists classify it as a water world, a term that barely captures the reality. An entire planet where the oceans might run hundreds of miles deep with no land in sight, just an abyss of liquid crushing down on a core of exotic high-pressure ice. What makes GJ-1214b so extraordinary is its atmosphere, or rather, its lack of a traditional one. Observations suggest this super-Earth is wrapped in a dense, hazy blanket of water vapor, hydrogen, and helium, so opaque that even our most powerful telescopes struggle to peer beneath it. Surface temperatures hover around 200 degrees Celsius, hot enough to keep water liquid but far too intense for Earth-like life. Yet here's the twist: beneath that scalding steam could lie an ocean unlike anything in our solar system. Not the familiar, salty waters of Earth, but a fluid so compressed by the planet's gravity that it transitions seamlessly into exotic states. Supercritical water where liquid and gas blur, or even layers of electrically conductive ice deeper down, squeezed into crystalline forms that don't exist naturally on our world. Comparing GJ-1214b to Hycean planets like K2-18b reveals a stark contrast. Both are water-rich, but where K2-18b's hydrogen-rich atmosphere might cradle life in its upper layers, GJ-1214b's steam-shrouded depths are a crucible of extremes. The pressure here would be unbearable, thousands of times greater than Earth's deepest ocean trenches, enough to collapse submarines like crumpled paper. Yet extremophiles on Earth thrive near hydrothermal vents under similarly brutal conditions, feeding on chemical energy rather than sunlight. If life exists on GJ-1214b, it wouldn't be photosynthetic algae or swimming creatures, but something far stranger. Microbes clinging to geothermal vents in the abyss, their biochemistry adapted to a world where water behaves like molten metal. The real mystery is how this planet formed. Did it start as a mini Neptune, losing its hydrogen envelope over time, or was it always a waterlogged giant? Some theories suggest it might have migrated inward, its original ice vaporizing into the steamy shroud we see today. Others propose it's a cosmic rarity, a world that formed with far more water than Earth, perhaps from a bombardment of icy comets in its youth. Every hypothesis paints a different picture: a transient oasis slowly boiling away, or a stable, if hellish, ecosystem that's endured for billions of years. Studying GJ-1214b is like trying to decipher a message written in fog. The James Webb Space Telescope has glimpsed chemical hints, traces of water vapor and possibly methane, but the planet's thick haze keeps its secrets locked away. Future missions might deploy specialized instruments to analyze its deeper layers, searching for molecules like hydrogen sulfide or ammonia that could hint at active geology or even biology. Until then, this world remains a tantalizing enigma, a reminder that habitability isn't always about comfort. Sometimes it's about resilience, the ability to endure in places where the very laws of physics seem rewritten. And if life can cling on in the crushing depths of K2-18b, then the galaxy's definition of home might be far stranger and far more wondrous than we ever imagined. 36 light-years from Earth, orbiting a star just visible to the naked eye in the constellation Vela, spins a planet that pushes the limits of what we consider habitable HD 85512b. This super-Earth, nearly 3.5 times the mass of our own world, dangles precariously at the outer edge of its star's Goldilocks zone. One misstep, a slightly wider orbit, and it would be a frozen wasteland. One step closer, and it could bake under a runaway greenhouse effect. But right here, balanced on this knife's edge, HD 85512b teeters between possibility and desolation, offering scientists a masterclass in cosmic fine-tuning. The star at the center of this system is no ordinary red dwarf. HD 85512 is a K-type orange dwarf, older, quieter, and more stable than the flare-prone M dwarfs that dominate exoplanet discoveries. Its gentle glow gives off just enough warmth to keep water liquid on planets orbiting relatively close. But HD 85512b's position is so borderline that early climate models sparked heated debates. Some simulations suggested it might be a snowball world, its oceans locked under miles of ice. Others proposed that a thick atmosphere could trap enough heat to maintain temperate pockets, especially near the equator. The truth likely lies somewhere in between a planet of extremes, where survival depends on delicate atmospheric balancing acts. That atmosphere is the real wild card. With gravity 50% stronger than Earth's, HD 85512b almost certainly holds onto a dense, swirling shroud of gases. The problem: density doesn't always mean habitability. If this atmosphere is rich in carbon dioxide, a likely scenario given the planet's volcanic potential, it could create a suffocating greenhouse effect, turning the surface into a pressure cooker of scorching winds and acid rain. Alternatively, if nitrogen dominates, the climate might stabilize into something more forgiving, with cyclones redistributing heat from the perpetual daylight side to the frigid night side. Then there's the star's faintness. HD 85512 emits only 20% of our sun's visible light, meaning photosynthesis, if it exists here, would need to adapt to a dim, orange-tinged world. Plants might evolve black or purple pigments to absorb every possible photon, or life might retreat underground, relying on geothermal vents rather than sunlight. The very rhythms of this planet would feel alien. Years that blur by in 58 Earth days, seasons dictated by atmospheric tides rather than axial tilt, and weather systems so vast they could encircle continents. What makes HD 85512b so compelling isn't just its precarious position, it's the reminder that habitability isn't a checkbox but a spectrum. This world forces us to ask, how thin can the line between too hot and too cold truly be? And if life can cling to existence here at the ragged edge of a star's warmth, then the universe might be far more inventive and far more stubborn than we ever dreamed. 12 light-years from Earth, circling a star almost indistinguishable from our own sun, orbits a world that keeps astronomers arguing, Tau Ceti. This enigmatic planet sits in the so-called optimistic habitable zone of its star, a region where liquid water might exist under the right conditions. But here's where the debate ignites. Is Tau Ceti a rocky super-Earth with continents and oceans, or a gaseous mini-Neptune with no solid surface at all? The answer could redefine our understanding of habitability around sun-like stars. Tau Ceti itself is a cosmic mirror, a G-type yellow star nearly identical in size and brightness to our Sun, but with one unsettling difference. It's surrounded by a sprawling debris disk 10 times denser than our solar system's asteroid belt. Picture a celestial shooting gallery where comets and asteroids crisscross unpredictably, raising the odds of catastrophic impacts. For Tau Ceti, That means a history of violent collisions, events that could have vaporized early oceans or, paradoxically, delivered the water needed for life. Some models suggest the planet might be a battered wasteland, its surface scarred by relentless bombardments. Others propose that its massive size, 4 times Earth's mass, could have shielded it, with gravity holding onto a thick atmosphere that protects against impacts like a planetary force field. Then there's the temperature puzzle. Tau Ceti e orbits closer to its star than Earth does, completing a year in just 168 days. Without an atmosphere, surface temperatures would soar to a blistering 70 degrees Celsius, too hot for liquid water. But if this world has a carbon dioxide-rich shroud similar to early Mars, it might trap just enough heat to create temperate zones, the darker possibility. A Venus-like runaway greenhouse effect, where the air is so thick it turns the planet into a pressure cooker, with lead melting temperatures and sulfuric acid clouds. The real intrigue lies in the planet's composition. Tau Ceti E's density measurements hover ambiguously between rock and gas, leaving scientists at an impasse. If it's a super-Earth, its strong gravity could sustain active volcanoes and tectonic plates, recycling gases and regulating climate over eons. But if it's a mini-Neptune, any hope of a solid surface vanishes beneath layers of hydrogen and helium. The James Webb Space Telescope might soon settle the debate, analyzing starlight filtered through Tau Ceti E's atmosphere, if one exists for hints of water vapor or methane. What makes this system so compelling isn't just the planet, it's the star's eerie familiarity. Tau Ceti is one of the closest solar twins to Earth, a neighbor so similar it's been the setting of countless sci-fi stories. Yet its debris-choked environment paints a stark contrast to our orderly solar system. If life does exist on Tau Ceti E, it wouldn't be the lush paradise of fictional tales, but a tenacious survivor in a chaotic cosmos, a testament to nature's ability to carve out hope in the unlikeliest of places. Every observation of this contradictory world whispers the same question: is habitability the exception or a rule that bends in ways we're only beginning to understand? 260 light-years away, circling a star almost indistinguishable from our own sun, drifts a world that ticks nearly every box in the search for Earth's twin Kepler-1638b. This isn't just another exoplanet lost in the data. It's a rarity among rarities, an Earth-sized gem orbiting squarely in the habitable zone of a G-type star, the same stellar classification as our Sun. What makes this planet so extraordinary isn't just its size, just 10% larger than Earth, but its orbit, 259 Earth days of steady, sunlit seasons, a rhythmic dance so familiar it feels almost like home. Picture standing on Kepler-1638b's surface. The sun in the sky wouldn't look all that different from our same golden hue, same reassuring steadiness. But the view beneath your feet might be another story. With gravity slightly stronger than Earth's, landscapes could be more dramatic. Taller mountain ranges, deeper canyons sculpted by tectonic forces over billions of years. The real magic, though, lies in the possibilities of its climate. Unlike the chaotic swings of planets around red dwarfs, Kepler-1638b's orbit is stable enough to avoid extreme temperature shifts. Models suggest that with an Earth-like atmosphere, this world could maintain liquid water across vast regions, with weather patterns not unlike our own, ocean currents distributing heat, seasons cycling predictably, and polar ice caps ebbing and flowing with the years. But here's the catch: finding planets like this is like spotting a needle in a galactic haystack. G-type stars like Kepler-1638 are outnumbered by their smaller, dimmer cousins, red dwarfs, which make up 75% of the galaxy's stellar population. Yet red dwarfs are volatile, prone to flares that strip away atmospheres, while sun-like stars offer something priceless: stability. Over billions of years, their gentle radiation doesn't just allow life to emerge, it gives life time to evolve into complexity. Kepler-1638b star is middle-aged, around the same stage as our Sun, meaning any potential biosphere here has had the cosmic equivalent of a full, uninterrupted childhood to develop. The discovery of this world was a triumph of patience. Detecting Earth-sized planets around Sun-like stars is notoriously difficult. Their transits are faint, their orbital periods long. Kepler-1638b was hiding in plain sight, its signal buried in noise until advanced algorithms teased it out. Now it stands as one of the most promising Earth analogues we've found, a benchmark for what to look for in future searches. The question now is what fills the gaps in our knowledge. Does Kepler-1638b have an atmosphere? If so, is it thick with nitrogen like Earth's, or a suffocating blanket of carbon dioxide like Venus? Telescopes like the James Webb Space Telescope are poised to answer these questions, analyzing the starlight that filters through the planet's potential air layers. Every molecule detected water vapor, oxygen, methane, would bring us closer to understanding whether this distant world is a barren rock or a living, breathing counterpart to our own. Kepler-1638b isn't just a scientific target, it's a mirror held up to Earth, reflecting back the delicate balance that makes our planet habitable. Its existence whispers a tantalizing possibility that around stars like ours, in orbits like ours, worlds like ours might not be the exception, but the quiet, unassuming rule. 12 light-years from Earth, a world drifts in quiet equilibrium Lighton B. This super-Earth, nearly 3 times our planet's mass, orbits a star so faint it's invisible to the naked eye, yet its potential for habitability makes it one of the most compelling targets in the search for life. What sets Lighton B apart isn't just its proximity, practically next door in cosmic terms, but the remarkable stability of its dim red dwarf host. Unlike the stormy tantrums of Proxima Centauri or TRAPPIST-1, Lighton's star is a cosmic pacifist, emitting barely a flicker of the flares that typically sterilize nearby planets. That serenity could be the key to this world's survival. Lighton B's tidal locking is inevitable, one hemisphere forever bathed in the star's dull crimson glow, the other locked in perpetual night. At first glance, that sounds like a recipe for extremes, a scorching desert on the day side, a frozen wasteland on the other. But climate models reveal a tantalizing middle ground. With even a modest atmosphere, heat could circulate from the perpetual twilight zone, creating a ribbon of temperate real estate where temperatures might hover near Earth. Picture a world where the sun never moves in the sky, casting long shadows over landscapes where rivers flow under ruby-hued light and glaciers creep inward from the dark side. The real intrigue lies in the star's history. Most red dwarfs spend their youth bombarding planets with radiation, but Lighton's star has always been quiet. Observations spanning decades show no significant flares, no violent outbursts, just a steady, faint pulse. For Lighton B, that could mean holding onto an atmosphere for billions of years, a rarity in red dwarf systems. Some simulations suggest it might even have seasons, driven not by axial tilt but by atmospheric tides that shift moisture between hemispheres. This world hasn't escaped the notice of those hunting for extraterrestrial intelligence. The Breakthrough Listen project has trained its radio telescopes on Lighton's star, scanning for artificial signals amid the cosmic static. While no transmissions have been detected, the very act of looking reshapes the possibilities. If a civilization did arise here, it would face unique challenges, building under a stationary sun, harnessing energy from a dim star, or perhaps living deep underground to avoid radiation. Lighton B stands as a testament to cosmic moderation. In a universe where most habitable zone planets orbit turbulent stars, this world offers something rare, a chance for balance. It's a reminder that life, if it exists out there, might not need perfection, just patience and a star gentle enough to allow it to endure. 770 light-years from Earth, tucked into the constellation Cygnus, orbits a world that dances on the edge of possibility, Kepler-1629b. This rocky planet, just 40% larger than Earth, circles a dim red dwarf star with a rhythm that places it squarely in the habitable zone where temperatures could allow liquid water to pool on its surface. But here's what makes this world extraordinary. It doesn't just orbit in the right place, it might have the armor to survive its star's fury. Red dwarfs like Kepler-1229 are notorious for their volatility, frequently unleashing flares that blast nearby planets with enough ultraviolet radiation to strip away atmospheres over time. Yet Kepler-1229b's sheer size could be its saving grace. With a mass roughly double Earth's, its gravity might be strong enough to cling to a thick atmospheric blanket, one that could act like a planetary radiation shield. Picture an ozone layer on steroids, deflecting deadly stellar flares while trapping just enough heat to keep the surface temperate. Climate models suggest that with the right mix of gases, carbon dioxide for insulation, nitrogen for stability, this planet could maintain liquid water despite its star's tantrums. But the real intrigue lies in its potential for twilight resilience. Like many planets orbiting red dwarfs, Kepler-1229b is likely tidally locked, with one side perpetually bathed in faint crimson light and the other shrouded in eternal night. Yet a dense atmosphere could work like a global heating system, circulating warmth from the day side to the night side through relentless wind patterns. The result, a narrow band along the terminator line where day meets night, might offer the perfect equilibrium, neither scorched nor frozen, but a temperate in-between where water could flow and life might cling on. The James Webb Space Telescope could soon unveil this planet's secrets. If traces of water vapor or methane linger in its atmosphere, they'd hint at active geology or even biology. But the stakes are higher than one world. Kepler-1229b is a test case for whether red dwarf systems, which make up 75% of the galaxy's stars, can be more than cosmic dead zones. If this planet proves that a thick atmosphere can defy stellar radiation, the universe's habitable real estate just got a lot bigger. Kepler-1229b isn't just a distant dot of light, it's a lesson in cosmic endurance. A reminder that even in the harshest neighborhoods, nature might find a way to carve out refuge. And if life can thrive here, under the flickering glow of a tempestuous star, then the galaxy's quietest corners could be teeming with worlds we've only begun to imagine. Gliese 581g might be the most controversial world in the search for habitable exoplanets, a planet that, depending on who you ask, either doesn't exist at all or could be one of the most promising candidates for life beyond Earth. Discovered in 2010, this super-Earth was initially hailed as the first exoplanet found squarely in its star's Goldilocks zone, a world with just the right conditions for liquid water to flow on its surface. But within months, other astronomers challenged the data, arguing that the planet was nothing more than a ghost in the noise of stellar activity. The debate still rages today, turning Gliese 581g into both a scientific puzzle and a cultural icon. At the heart of the controversy is its star, a dim red dwarf just 20 light-years from Earth. Gliese 581 is a quiet star by cosmic standards, but its planets orbit so tightly that their gravitational tugs are subtle, buried in the star's own flickering rhythms. The initial discovery team, led by astronomer Stephen Vogt, used years of painstaking observations to tease out a signal they claimed was Gliese 581g. A rocky world about 3 times Earth's mass, tidally locked to its star, with one side perpetually bathed in faint crimson light and the other shrouded in eternal darkness. Climate models suggested that with a thick enough atmosphere, heat could circulate to create a twilight belt of temperate conditions, a narrow band where water might pool and life could take root. But skeptics fired back. Another team, analyzing the same data, found no trace of the planet. They argued that what Vogt's team interpreted as a planetary signal was actually just the star's own variability, sunspots or magnetic activity masquerading as gravity's pull. The disagreement wasn't just academic, it struck at the limits of detection methods. Gliese 581g, if real, would be a triumph of precision. If not, it was a cautionary tale about the challenges of finding Earth-sized worlds in the data, yet the planet's cultural impact outran the science. Long before its existence was disputed, Gliese 581g became a beacon in the search for extraterrestrial life. In 2008, a team beamed a radio message toward the star, a digital time capsule of human art and music aimed at the planet's hypothetical inhabitants. The project, called A Message from Earth, was more symbolic than practical. The signal wouldn't arrive for 20 years, and any reply would take just as long, but it captured imaginations. Here was a world close enough to reach, strange enough to fascinate, and just maybe habitable enough to dream about. The arguments over Gliese 581g's existence forced astronomers to sharpen their tools. New techniques like Bayesian analysis and machine learning were deployed to sift through the noise. Some studies tentatively revived the planet's prospects, finding faint hints of its signal in reanalyzed data. Others doubled down on its absence. The truth might remain unresolved until next-generation telescopes can stare directly at the system, searching for the faint heat signature of a world that, for now, exists in the liminal space between discovery and myth. What makes Gliese 581g so compelling isn't just the science, it's the audacity of the question it forces us to confront. How do we define a habitable world when even its existence is uncertain? And if we one day confirm it's real, what does that mean for the countless other borderline detections lurking in the data? This disputed planet, whether phantom or pioneer, reminds us that the search for life is as much about patience as it is about proof. The universe holds its secrets close, revealing them only when we're ready to look harder, think deeper, and dare to question even our own discoveries. K2-18b isn't just another exoplanet lost in the cosmic census, it's a time traveler. Orbiting a star 1,700 light-years from Earth, this super-Earth is a relic from an era when the universe was nearly 3 billion years younger, part of a system that's endured for almost half the age of the cosmos itself. What makes this world extraordinary isn't just its size, twice Earth's mass, but its star, a K-type orange dwarf, a celestial workhorse that's outshone its red dwarf cousins in longevity and stability. While most habitable zone planets we found orbit volatile red dwarfs, K2-18b enjoys a gentler rhythm, basking in the steady glow of a star that's neither too hot nor too prone to tantrums, but just right for nurturing life over geologic timescales. Picture a year on this distant world, 130 Earth days of amber-lit seasons, dictated by an orbit slightly tighter than Venus's in our solar system. At first glance, that proximity might seem too toasty for liquid water, but here's the twist: K-type stars like Kepler-283 are cooler than our Sun, meaning their habitable zones snuggled closer in. For Kepler-283c, that translates to Goldilocks conditions, a sweet spot where sunlight isn't so weak that oceans freeze, nor so intense that they boil away. Climate models suggest that with even a modest atmosphere, this planet could maintain surface temperatures remarkably similar to Earth's. The catch: its gravity, 20% stronger than ours, would sculpt landscapes with deeper valleys and more towering peaks, while potentially holding onto an air so dense it would scatter sunlight into perpetual golden hour hues. The real magic lies in the star's endurance. K-types are the marathon runners of the stellar world, burning fuel so efficiently they can shine for 50 to 70 billion years, far outlasting our Sun's 10 billion-year lifespan. For Kepler-283c, that means an almost unfathomable head start. While Earth's biosphere has had a mere 4 billion years to evolve, life here, if it exists, could have been refining itself for twice that long. Imagine organisms adapted to the star's dimmer light, perhaps with pigments tuned to harvest orange photons, or ecosystems thriving in subsurface aquifers kept liquid by geothermal heat. The possibilities stretch the imagination, hinting at forms of biology that have had epochs to perfect survival in ways we can't yet conceive, yet challenges remain. K2-18b star, while stable, still emits enough ultraviolet radiation in its youth to threaten nascent atmospheres. Unlike the flare-prone red dwarfs that dominate exoplanet discoveries, this star's early tantrums would have been milder but persistent, like a slow burn rather than a series of explosions. The planet's saving grace might be its sheer resilience. With twice Earth's mass, its core could still be churning with geologic activity, replenishing lost gases through volcanic outgassing or plate tectonics. Some models even suggest that its original water supplied, delivered by icy comets during the system's chaotic infancy, might have survived, pooled in vast subterranean reservoirs or locked beneath icy crusts. What truly sets this system apart is its quiet confidence. While red dwarf planets dominate headlines for their sheer numbers, K2-18b represents a rarer class, a world where time isn't a limiting factor but a canvas. Around this ancient star, evolution wouldn't need to rush. It could unfold at a pace we'd find incomprehensible, with genetic trial and error spanning epochs longer than Earth's entire fossil record. If life here follows anything like the trajectory of our own planet, the results could be staggering. Civilizations risen and fallen a dozen times over, or technologies forged across spans of time that dwarf human history. The lesson of K2-18b isn't just about one planet, it's about redefining what we consider a promising habitat. In a cosmos where most searches focus on Earth twins around sun-like stars or turbulent red dwarf survivors, this world whispers a third option: the quiet achievers. The ones that won't flare into oblivion or fade too soon, but endure, steady and patient, offering life a chance to experiment on scales we're only beginning to imagine. As telescopes like James Webb turn toward these ancient systems, we might find that the universe's greatest masterpieces aren't the loud or the flashy, but the ones that have learned the art of persistence. 17 light-years from Earth, tucked quietly into the constellation Eridanus, orbits a world that could redefine our understanding of habitable red dwarf planets GJ3323b. This isn't just another exoplanet lost in the sea of discoveries. It's a cosmic anomaly, a temperate world basking in the gentle glow of one of the quietest red dwarfs ever observed. While most planets orbiting these small, dim stars face relentless stellar fury, GJ3323b exists in rare equilibrium with surface temperatures eerily similar to Earth's if it has the right atmosphere. The numbers alone make this world intriguing. Orbiting its star every 5.4 Earth days, GJ3323b is tidally locked, with one side forever facing the star's faint crimson light and the other shrouded in eternal night. But here's where it defies expectations. Climate models suggest that even with tidal locking, a moderately thick atmosphere could circulate enough heat to prevent extreme temperature swings. The day side might hover around a breezy 20 degrees Celsius, while the night side could stabilize at -10, creating a twilight zone where conditions are just right for liquid water. What truly sets this planet apart is its star's unusual calm. Red dwarfs are notorious for their violent youth, bombarding nearby planets with radiation that strips away atmospheres over time. Yet GJ3323's star emits barely a flicker of flares, making it a cosmic pacifist among its turbulent peers. For a planet this close, just 5% of Earth's distance from the Sun, that serenity could be the difference between a sterile rock and a world with the right ingredients for life. The real excitement lies in GJ3323b's accessibility. At 17 light-years, it's practically next door in interstellar terms, placing it squarely in the crosshairs of next-generation telescopes. The James Webb Space Telescope could soon analyze starlight filtering through its potential atmosphere, hunting for traces of water vapor, carbon dioxide, or even methane, molecules that would transform this world from a tantalizing "what if" into a concrete candidate for habitability. But the mysteries run deeper. How did K2-18b form with such Earth-like temperatures so close to its star? Was it born with a thick atmosphere that survived the star's early tantrums, or did it migrate inward later, avoiding the worst of the stellar storms? Every answer leads to more questions, painting a portrait of a world that challenges our assumptions about where life could take root. K2-18b isn't just a scientific target, it's a test of resilience. If this planet, against all odds, has held onto the delicate balance of air and warmth under the dim light of a red dwarf, then the galaxy's quiet corners might hide far more habitable worlds than we ever dared to imagine. And as we turn our telescopes toward this nearby neighbor, we're not just studying a distant dot of light, we're probing the very boundaries of what makes a planet a home. 820 light-years away, tucked into the constellation Cygnus, orbits a world that tests the limits of Earth-like potential Kepler-1652b. This isn't just another exoplanet lost in the sea of data. It's a rocky mirror of our own world with a radius just 12% larger than Earth's, circling a dim red dwarf in the elusive sweet spot where liquid water could exist. But what makes this planet truly remarkable isn't its size or position, it's the star it calls home. Kepler-1652 isn't a typical red dwarf. It's a cosmic metal giant packed with heavier elements like iron and silicon, a trait that might have shaped this planet's destiny from the moment it formed. High metallicity, the abundance of elements heavier than hydrogen and helium, turns out to be a game-changer for red dwarfs. Stars like Kepler-1652 didn't just sprinkle their planetary nurseries with dust, they showered them in the building blocks of rock and metal. Think of it like baking a cake with extra flour. The result is denser, sturdier. For Kepler-1652b, this could mean a planet richer in minerals, with a thicker crust or even a more robust magnetic field to deflect its star's radiation. But there's a trade-off. While metal-rich stars tend to birth more rocky planets, they also crank up stellar winds, potentially sandblasting atmospheres away over time. So the question isn't just whether this world could be Earth-like, it's whether it's managed to hold onto the ingredients for life against the odds. Then there's the tidal locking problem. Like most planets orbiting red dwarfs, Kepler-1652b is almost certainly locked in place, with one hemisphere perpetually baked in dull crimson light and the other plunged into eternal night. The day side might sizzle at temperatures fit for a desert, while the night side could freeze into a glacier-covered wasteland. But here's where nature throws us a curveball. The Terminator line, the razor-thin border between light and dark, could be a Goldilocks zone all its own. Picture a world where civilization clings to a ring of perpetual twilight, where the sun never rises or sets but hangs eternally on the horizon, casting long shadows over rolling landscapes. Climate models suggest that with the right atmosphere, heat could circulate from the scorching day side to the frozen night side, creating a narrow band of temperate real estate along this twilight strip. Winds might howl across the Terminator, carrying warmth and moisture to valleys and plateaus where liquid water could pool. Some simulations even predict sprawling ice caps on the night side, feeding rivers that trickle into the habitable zone, a stark contrast to Earth's climate, but no less viable for life. The real wild card is time. Red dwarfs like Kepler-1652 live for trillions of years, meaning this planet has had far longer than Earth to experiment with chemistry and biology. If life did emerge here, it would have faced a gauntlet of challenges: radiation from the star's turbulent youth, the slow erosion of its atmosphere, the stark divide between its light and dark halves. Yet extremophiles on Earth thrive in places just as hostile, from volcanic vents to Antarctic ice. The lesson: habitability isn't about perfection, it's about persistence. Kepler-1652b forces us to rethink what makes a world Earth-like. It's not about matching our planet feature for feature, but about finding the resilience to carve out habitability in the unlikeliest of places. As telescopes grow sharper, this distant world, with its metal-rich star and twilight ecosystems, might just teach us that life doesn't need a sunny blue sky to flourish. Sometimes all it needs is a sliver of balance on the edge of forever. From scorching Hycean worlds shrouded in golden haze to rocky super-Earths basking in temperate twilight, these 25 planets defy simple categorization. Each one tells a different story of resilience in the face of stellar fury, of delicate climate balances on tidal-locked worlds, and of atmospheres clinging to existence against cosmic odds. Some, like Kepler-1638b, resemble Earth in size and orbit, offering familiar rhythms under alien suns. Others, like K2-18b, rewrite the rules entirely, with global oceans dissolving into thick hydrogen blankets under crushing pressures. The diversity is staggering. Red dwarf survivors like Ross-128b, quietly enduring for billions of years, and eccentric outliers like HD-40307g, where elliptical orbits create seasons of fire and ice. Yet for all their promise, confirming true habitability remains one of astronomy's greatest challenges. A planet can tick every box, right size, right orbit, even atmospheric water vapor, and still harbor lethal surprises, toxic chemistry, sterilizing radiation, or runaway greenhouse effects. Our tools are still blunt instruments, parsing starlight for molecular hints like detectives, reconstructing a crime scene from scattered shadows. The James Webb Space Telescope has already transformed the hunt, but even its infrared eyes can't reveal surface conditions or active biospheres. What we need next are direct images of exoplanet atmospheres, spectroscopy precise enough to spot industrial pollutants or chlorophyll-like pigments, and one-day interstellar probes venturing close enough to sniff the air of these distant worlds. The coming decade will redefine the search. Missions like the Habitable Worlds Observatory and the European Extremely Large Telescope will peer deeper, analyzing atmospheric compositions with unprecedented clarity. Meanwhile, projects like Breakthrough Starshot aim to send feather-light probes hurtling toward Proxima Centauri at a fraction of light speed, potentially returning data within our lifetimes. Every technological leap brings us closer to answering humanity's oldest question. Are we alone? Stay curious. The cosmos has already shown us that habitable conditions emerge in the unlikeliest places, around dying stars, in multi-star systems, even in the frozen outskirts of solar systems. As we uncover more worlds, we're not just expanding a catalog, we're learning how fluid the recipe for life might be. Follow each discovery, because one day, perhaps sooner than we think, a speck of light in a telescope's eyepiece will reveal something unmistakable, the shimmer of another living world. Until then, the search itself is the story, and every new planet a chapter waiting to be written.